Hello.
I think we're live.
Yep.
Hello, everyone. Welcome to today's brand new episode of Courtcast. I am your host, Tim.
Mikey.
Sahil, welcome everybody to a brand new exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we mostly do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. So without further ado, let's get to it. So I guess Tim and Mikey, when I was first initially learning physics, I heard that there were four forces, which we'll get to very briefly, and depending on how much detail is on each one. And it seems like that formed a kind of, I guess, the base of that formed what we currently know about physics. But as we were talking before this episode, it seems like there might be a case for a fifth force, and whatever that means. So I guess before we dig into four fundamental forces as the groundwork, can we start off by describing what is a force? Mikey, I'm gonna point to you first.
I would say so. Typically, right, when we think of a force, we think of something that pushes or pulls on something. The most typical example we think of is like gravity, right? That was probably the first force that was ever discovered, and I think it was discovered like sometime around the time when monkeys evolved into humans. The gravitational force was discovered. I guess people realized that this was a thing. And later on, much later on, maybe like a few hundred years ago, the electromagnetic force. Actually, no, electromagnetic force was discovered, quote unquote. People have had magnets and known that like these weird rocks will attract other rocks and exerting a force on other things, like seemingly like magic, even though it's not touching the thing. So that's typically what we think of a force. But I think in a modern view, like it's a little bit more general than that. These days, I think most physicists would define a force as anything that causes change. And one way you can cause change is by, exerting a push or a pull on something. You're initiating a change in that object's position, its velocity when you're pushing or pulling on it. And so that's a kind of change. And so there's a force responsible for that. But anytime you see anything changing in some way, there is some force responsible for that. And I think that's probably the most general definition of a force.
I guess kind of double clicking on that, you mentioned that like in olden times, or maybe several centuries back, people had magnets and noticed that they were able to enact a force on something without touching it. Could we explain maybe like how that works? Like, for instance, if I push something physically with my hand, I'm touching it. But if I were to use like a magnet or maybe something else to like push something without physically touching it, how does that work? I guess Tim, I'll give this question over to you.
Yeah, I think we can borrow the understanding from electromagnetism, right? Like how does an electron feel the tug and pull of the proton? And the modern understanding is that there are these objects called electromagnetic field. It's basically telling you the attraction of this force is embodied in some sort of abstract object we call a field. It's sort of like a all permeating. I don't like to use the word, but some kind of a substance that permeates the universe, such that when a field exists, is not zero, then other particles can feel this tug and pull, and we can see this electromagnetic field very visibly, actually, in high school physics. For example, if you have a magnet and you put some kind of magnetic dust around it, iron filing, I think it's a classic experiment. You see that, or you put a compass near it, you see that the material tend to form like certain patterns, and you can almost kind of visually see those electromagnetic fields. And in fact, as the electromagnetic field changes, it goes up and down, left and right. These changes become light, particles of light. So light, really, when we see, that the sun is bright, you see the color of the trees. These are caused by electromagnetic fields, right? So this is the embodiment of electromagnetic forces. So I think it's safe to say that pretty much every force comes with their own force field. So for gravity, there's a gravitational field responsible for gravitational attraction. For electromagnetism, there's the electromagnetic field, and so on and so forth, and also for the other forces that we haven't described yet.
So Tim, can you say a force and a field are equivalent to each other, or how do I put force in the context of this field that you just described?
I think it is in particle physics, because ultimately particle physics is the study of fields, I think, and that's fair. A particle is simply kind of a disturbance in the field. I guess to kind of borrow some lingo from Star Wars. I mean, it's not too crazy actually. These nomenclature like force fields and all that.
Yeah, no, I just wanted to say though, it has nothing to do with like a limitation of particle physics in terms of narrowness. Like it's true, yes, for every single force there is a field. That's how you model every single force you can imagine. To say that there can be a force without a field associated with it would sound crazy, not just to a particle physicist, but to any physicist. There's always something, whenever there's a change happening, there's always something enacting that change, right? It's almost like communication, right? Like if I'm talking to Tim right now, it's not, there's actually a mechanism by which my mouth releases sound waves, goes into the phone, and travels through the internet, goes up to a satellite, comes back down. There's some connection there. And the field that Tim was talking about provides that connection. And we actually did an episode earlier. If you saw the episode about new particles, as Tim mentioned, there's for every single field, there's an associated particle. So there's literally a particle that's sending the message, pull, pull, push, push. So you can think about it like a kind of communication through some medium.
Is there only pull and push for forces, or are there like other things that it can be?
So far, what we know of is we know of pull, we know of push, and we know of change species.
Okay. Well, we can talk about maybe briefly what change species means in a little bit, but okay, that's an interesting terminology. So I guess kind of taking a step back, we've described a force. A force is effectively is responsible for anything changing. Is that fair to say?
If there's no forces, then nothing's changing.
Okay. So
sure.
that's fair. So now coming to the four fundamental forces as they're called, can we describe in this context of change what I guess each of them do in per se? So starting with gravity.
Yeah, I think we got to mention one thing though. So for each of the forces, only except gravity, only a subset of particles kind of participate to those changes.
Yes, gravity is the only force that is felt by everybody.
Yeah. So gravity is responsible to tuck and pull of just energy itself, mass and energy, right? So that's gravity. And electromagnetism is responsible for the pushing and pulling of things that have electromagnetic charges, right? So if you're a neutron, you don't have electromagnetic charges, you don't exactly participate in the electromagnetic force. And then there's the weak force, which is responsible for changing certain species of particles within a nucleon. And people usually are not so familiar with it because we don't see that everyday lives. Because if a proton is changing to neutron all the time, we'll have nuclear explosions everywhere, and that's not good for everyday life. So obviously, we don't see that very often. So the weak force is somewhat hidden. We don't see it very much. And the strong force is responsible for the binding of nucleons. We also don't see it very much because the strong force is very darn strong. Like the protons and neutrons are really stuck together, and the quarks within them are very much stuck together. So that roughly summarizes kind of the four forces that we know exist.
Great summary.
I want to quickly paraphrase the weak and strong force and make sure my understanding is matched. So weak force, an example of this could be like neutron decay. So as far as I know, neutrons last by themselves for about 12 minutes, 11, 12 minutes which is like a really long time in particle physics terms, and they decay into a proton, electron, and forget neutrino or antineutrino, 3 different particles. So that represents a change in, would you say, in the species of the particles? It's not that like
Yeah.
a neutron, let's say, was remaining stationary, and then it just decayed into like these 3 objects. That represents a change, and so that change is captured by the weak force. Is that a fair example?
Yep.
Okay.
Perfect.
And then for the strong force, one way to conceptualize it in my mind would be like, imagine you have like a part an atom with a lot of protons in like the nucleus. If there were no strong force, all of them would repel from each other. So it's basically a binding glue that like pulls everything together, and strong because it overcomes the electromagnetic repulsion between protons. Is that a fair example?
Yeah. In fact, I'll add on more to that. Not only would the protons and neutrons fall apart, the quarks inside the protons and neutrons would also fall apart. We wouldn't even have protons and neutrons in the first place. So it's a little more dramatic, but the gist is the same.
Fair. Okay. So then existence as we know it would not be there without the strong force. Okay, cool. So I think that gives a good summary of like the 4 forces. So I guess like before we talk about even a 5th force, that seems fine. Like, why do we need an extra force? Like these 4 things seem to describe like what we know. What's missing?
They do seem to describe what we know. I just wanted to point out that, like, okay, so the gravitational force, obviously, it's very apparent, right? Like people have known about that. Like even monkeys like know about it, right? The electromagnetic force, right? That probably would have required evolution into humans to like play with certain types of rocks and see that they exert a force. So those 2 forces we've known about, for ages. Um, the strong force wasn't really discovered until like the mid 1900s, and the true nature of the weak force wasn't even discovered until like even a couple decades after that. So as time goes on and as we explore physics, we are discovering that there are new forces that we didn't know existed. And so to me, it's kind of weird to assume that, okay, I guess it's just these 4 and that's the end of it. Like, how can that, like, we've discovered the 2 of them so recently. Um, I think it's just important to keep an open mind. And when you see this pattern of new discoveries of new forces, it's really hard to imagine that, that could be it.
Yeah, and also to add on to that, because the all 4 forces, as we've described, they look pretty different. Although there has been progress made to combine, for example, the weak force and the electromagnetic force. I think we had an older episode describing that. We don't really know how the strong force and the electromagnetic and the weak force are related. But then physicists do generally believe that all these forces are related. And in order to relate all of them together, it might necessitate the discovery of additional forces and force fields and force carriers. So there's every reason to believe that new forces are out there, maybe hidden because we don't have the technology yet to discover them. But my money would be on almost definitely there should be extra forces. Maybe not even just 5th, maybe it's the 6th, 7th, 8th, many
The
more.
infinite number of forces.
I guess then like why haven't we like seen a new force? Like what's going on? Like
Well, so we only see the ones that are obvious, right? And the 2 that are obvious, I guess, by human standards, are gravity and electromagnetism. Those are the obvious ones, right? Like everyone knows that we sit to the ground. Everyone has magnets in the refrigerator. Like you can see their effects very readily. The strong force and the weak force took so long to discover because their effects are very subtle. They're almost like hidden from our everyday experience. Um, and so that was kind of like a turning point, I think, when physicists realized, oh, like there can be bona fide forces that whose effects are just so small or in certain contexts kind of invisible to us. Who knows what else could be out there?
Yeah, I think in physics, there are quite a few ways to hide forces, and so far nature seems to take quite a few opportunities to hide some of the forces from us. And I think we can describe two of them that are pretty simple to understand. The first one could be that it could be like the strong forces. There could be new forces that are not that weak, but in order to see them, we might have to zoom in really close. And in order to zoom in really close, you might need a lot of energy to overcome the repulsion for that. And it's plausible that we just don't have enough energy in our accelerators to kind of zoom in that small of a distance yet. So that's possible, right? So that's one of the possible reason why some of the forces are hidden. And the other possibility is that maybe it's not that we don't have enough energy. Maybe we kind of have the wrong particles. Because remember, we were mentioning earlier, for many of the forces except gravity, only a subset of particles participate in those forces. Like, what if there's a new force and somehow we don't participate in those interactions, or maybe we participate very little, right? Then we won't see those forces, at least not yet, because we're not using the right particles to feel those forces. And this is starting to sound a little bit sci-fi, but these are the two possibilities. At least the main ones. There are probably others, but these are the two main ones, I think.
That's interesting. I would actually really like to dig into each one of those examples you gave, Tim. I guess at a high level, could you describe, like, let's say I like did a whole bunch of experiments and I came to you and I said, "Hey, Tim, I've discovered like a new fifth force." What would you need to see to be like convinced that this is like a new force?
I would say the definitive discovery is if you are able to jiggle the force field and you make a force carrier, a new particle, then voila, it's a new force, unambiguous. So that will be the definitive way to discover a new force. Of course, there could be other ways, but I think that's the gold standard in particle physics. Make a new particle that's associated with a force carrier, and it's a new force.
I guess, but then how would you be able to tell it's not associated with like a new like particle of like matter per se?
I think there's certain properties about force carriers that I don't think we should get into a little bit.
Okay.
That we can distinguish them by the properties of those set particles, but let's not go into details. It's a little more technical, but that the gist is there. Yeah.
Yeah, you can tell. Like certain properties of particles determine whether or not they kind of fall into the category of like matter particles or stuff, or like communicators of a force. And that's, at least in the framework of quantum field theory, that's like a very strict boundary. You can categorize those things just by looking at their properties, like their spin and other things that we shouldn't get into. But
Gotcha. So I guess I want to wait. Okay, so before we get into that, there's an audience question I want to ask.
yeah.
Said, are you talking about the fundamental four forces? If yes, I do believe gravity may not be a fundamental force and is more like an emergent behavior of the space-time. How would you respond to that?
Yeah, I think we take a pragmatic approach. I think so far the evidence points to that gravity is a force carrier, like you described. Is it not impossible that gravity might be made of something else? Is it not possible that maybe a messenger of gravity, the graviton, could be made of something smaller, hence emergent? It's possible, but we don't have the technology to kind of break up a graviton yet. So, given what we've observed so far, the scientific consensus is that there are four fundamental forces, and gravity, as far as we know, so far, it is fundamental.
Okay, but I think that the user might be referring to these theories of like Eric Verlinde about how like gravity can be derived from entropic considerations. And I just wanted to point out that in physics it kind of seems what's the word? It kind of seems unbelievable, but like two things can be true at the same time, even if they seem to contradict each other. It's a concept called duality. So even if it's true that, and we haven't done this yet. So, these theories about emergent gravity, they haven't been precisely written down yet. There are some intriguing hints that show that, gravity might be describable as some kind of like entropic dynamics, but it's certainly also describable through this force mediator picture. Both of those things can be true at the same time. And if both of those things are true at the same time, it's very intriguing because it means there's a connection between entropy and, quantum fields. So, these are interesting ideas. But just because it's one doesn't mean it's not the other, I would say.
Gotcha. So okay, so coming back to the 2 points you made, Tim, I want to zoom in on the first one, but pun not intended. But like talking about discovering new force carriers at higher energy, can we like break down like what does that mean like for our audience, like to like a layperson, like what does it mean to discover things at higher energy? What does that have to do with zooming in? And like yeah, and also like why not lower energies? Like what's stopping you from going even like lower energy? Why does it
So
always need to be higher?
yeah, I mean, so let's not talk about the lower energy part because that's actually the other portion, you know.
Ah, okay.
But let's talk about the higher energy part. It just means that so imagine the particle of light. A particle of
Mhm.
light, has a certain amount of energy, and from quantum physics, it depends on the wavelength, right? Like visible light has a certain amount of energy, and gamma or X-ray light has a high amount of energy. But for the messenger, the carrier of electromagnetic force, it's really easy to make a particle of light. For example, even if I were just waving my hand or I just turn on a flashlight, I create a light. It's so easy. There's almost there's no lower bound threshold to create these particles of light.
Mhm.
But certain forces, depending on their properties, may not be like that. For certain forces, you might have to overcome an initial barrier, and that in order to even create a a force carrier. And notable example is the weak force. I mean, I don't want to go into the details, but when the weak force was confirmed to be discovered, and the Nobel Prize awarded, we had to produce those force carriers in an accelerator, and the accelerator has to overcome that energy barrier, and the barrier end up being like 90 times the mass of the proton. You know, it doesn't sound like a lot, but from a particle perspective, one tiny particle has to overcome 90 times the mass of the proton. It's a lot to ask. So that takes a while. So this is one way a force can be hidden. It's just that it's really hard. It's really rigid. I guess the force field is really rigid, or it's really hard to jiggle it, to really feel those forces. I guess for lack of a better word. That's why they're hidden.
I see. So I guess like does it mean that like this force doesn't appear until you explore higher energies? Like you throw high like yeah, just like yeah, we'll get to a moment. What does it mean to explore like higher energies, like experimentally, for instance? But like if you don't explore higher energies, you don't see this force. It just as might as well not exist if you're operating at like lower energies.
Like, yeah, can I just say one thing? Like, I don't know if this is too technical, but like in physics, even if it is too technical, I think it's something worth sharing because it's like very, very inescapable. There's a fact about physics that higher energies means smaller distance, like shorter distances.
Mhm.
And the way to think about that is like imagine that you have like you're on a boat, right? And there's like a dock, right? And imagine there's like a tiny bump in the dock, right? Um, if I okay, so imagine that there's an actual dock, like a big dock sticking out of the shore.
Yeah.
When I um, float past that dock, I'm gonna send waves to it, and when those waves hit the dock, they'll reflect back in a certain pattern, and I'll be able to um, discern the shape of that dock based on how the waves are reflecting back at me, right? But if you shrink that dock to like, 1 centimeter big, then the waves will reflect back just as they would as if that thing wasn't there, right? So in order to resolve, if we assume that like everything is a wave, which is true, if you want to resolve a certain distance, you need shorter and shorter wavelength, but you need like more and more, uh, I guess, yeah, like scrunched up waves. If you're using a very long wave to detect something very small, you're not going to see it. If you want to see something small, you need a very scrunched up wave in order to resolve it, in order to see its effects. And in this context, scrunched up wave means high energy because there's this relationship between the size of a wave and its energy. The shorter wavelength means oscillating more furiously, means higher energy. So when we say high energy, we mean really probing short distances in exactly the same way you could imagine water waves crashing on a dock, if that makes any sense.
Yeah, that actually helps elucidate this further. So what you're saying though is like if forces do exist at higher energies or quote unquote shorter distances, it means that they would be hidden because if you're exploring at lower energies, your resolution of like how closely you're able to zoom in is only so much, and you can't necessarily zoom in further unless you're
Yeah.
putting energy into it. So you won't actually be able to for lack of a better word, see in quotes the force.
Yeah, so trying to resolve like a hidden force is a lot like trying to resolve like a tiny bump in on the side of like a dock, with the waves from a boat. It'd be very hard. You have to look very closely, see like a very subtle pattern, maybe a subtle difference in the way the waves reflect back
Yeah.
at you.
That makes sense.
Yeah.
Oh, Tim.
Yeah, and also, I mean, some of our audience might ask the question, well, why do we care if they have these forces? You know, you can argue that, oh, the universe doesn't have so much energy anymore, and the universe is very large, so maybe we don't really care about those forces. But remember, the universe used to be a lot smaller, and there used to be a lot more energy packed into, the same volume, I guess it's a fixed volume of universe. So if there were new forces, that means those new forces participated during the creation of the universe, during the Big Bang. And that means it did play a role, maybe not anymore these days, but it did play a role in how the universe began. And uncovering those new forces could change our understanding of how everything came to be. So it is important.
Yeah, but even if you're not like, artistic and poetic about, waxing poetic about the history of the universe, I just saw the movie Oppenheimer, and I just thought there's one line from that movie where they were like, we have to unleash the strong force before the Nazis do. Like the atomic bomb, where does that energy come from? It comes from the strong force. You're basically, when they discovered the strong force in the 50s, oh, sorry, I guess it's like, well, I guess they didn't really figure out its character until like the 70s. But when they first saw its effects, in the 1930s, one of the first things people realize is you could leverage this to make an insanely destructive weapon. And I think, at least if you're on the government, military, political side, like that's your main interest in discovering new forces. The fact that you might be able to use them to draw some kind of energy out. So, the discovery of new forces usually heralds some kind of revolution in technology. That's probably the most negative, evil example of it. But, understanding of forces in general typically leads to some kind of technological revolution.
That's an interesting perspective. So going to the other side, we've talked about like, throwing as much energy and seeing if forces exist at smaller distance scales. What about the opposite? Like if you have less energy and seeing if forces exist at larger distance scales, like really large distance scales.
So
I don't
Does
know
that
if
ever happen, Tim?
no, I
Can't
think
think of an example.
that's super intriguing, and that's plausible. But of course, you can argue that when you have really low energy stuff, then you're talking about really large distance. So Mikey's example applies. If you have really large energy, these are really tiny. You're talking about things at a microscopic scale. But when you talk about really low energy, then these are really large distance scale stuff. And you can argue that, if such a fifth force exists, it could even affect the structure of the universe right now. But of course, the question is, how come we haven't seen it yet? If there is a fifth force in between my hands, for example, or what the heck? Like, why am I not feeling it? Why am I not shooting lightning out of my fingers, right? I don't know, like sci-fi-esque style. Well, of course, you know, if there's a fifth force, it has to conform to our experiments. Our experiments were valid, so it has to explain that. So one reason is because we simply are made up of the wrong stuff, so we don't feel the forces. But guess what? The stuff that we know and love, baryonic matter, only makes up of 5% of the energy budget of the entire universe. 25% of it is dark matter. So dark matter is a great candidate to be able to feel the extra fifth force. So that's where this research is very tantalizing. It's very plausible that there's a fifth force, and dark matter is using it, is leveraging it. Dark matter really feels the fifth force, but somehow we don't feel it because we're not part of the club, so to speak, right? And that could really have a drastic effect. It could, because dark matter makes up so much of our universe. A fifth force for dark matter could change those properties of the big structure of the universe.
Tim, just to clarify, when you said the word baryonic matter, you're talking about like the matter that we see like in the visible universe. Is that
regular
correct?
stuff?
Regular stuff, the conventional stuff, protons, electrons, neutrons, and stuff. Yeah.
Gotcha. So I guess like so you're saying dark matter could experience like, I guess is this just means a force that doesn't interact with light, or like what do you mean something that we don't interact with, that we're not in the club? What makes this like fifth force in this low energy context like unique in some sense? Like, is it not interacting via light?
We know for sure that dark matter doesn't interact with light, or if it does, it's very weakly. That's why we call it dark, because it doesn't interact with light, dark light. But there is this possibility that like the dark matter interacts with itself, the whole different set of forces that we've never discovered. Like, so in this, like Tim mentioned earlier, like the neutron doesn't feel the electromagnetic force, right? It's completely blind to it. It's possible that we have our own set of forces that we interact with, and basically a lot of that is light, the electromagnetic force, and we know that there's this other stuff that doesn't interact with light, but who knows what that interacts with within itself, right? So it's like almost like two separate, like clubs, I guess, to use Tim's language.
Yeah, and I also want to add that it doesn't have to be dark matter either, right? Because most of the stuff that we have experimental data on, they're like electrons and protons and neutrons, or the quarks that make up
stuff in our club.
Yeah, this like the stuff that in the human club is the stuff that we've experimented with. So technically, some of the more exotic particles like muons, probably many of our audience might not be familiar with, or the tau lepton, or neutrinos, it's plausible that they could feel a different set of forces. There could be forces that only they participate in, but we don't. Of course, we have some experimental data to tell us how much fifth force or not fifth force they might or may not feel. But still, the data is not that great. There still is a plausibility that even some of the visible matter could feel extra forces in addition to dark matter and maybe other particles we haven't found yet.
Gotcha. I guess like then that leaves the 75% elephant in the room, this so-called dark energy. Could that be a fifth force? Actually, before we answer that question, can you give like a one sentence description of what dark energy is? Just super duper high level. Just one sentence. Mikey, I'm going to point to you since you look.
It does seem like dark energy could be a candidate for a fifth force, because as we mentioned in our podcast last week, right, there's something causing the universe to expand, and obviously that's a change. But dark energy, I think, fits, as far as our current understanding goes, fits firmly in the category of the gravitational force. We know the gravitational force given certain configurations of energy, we know that the gravitational force can cause this kind of repulsive expansion of space, and as a result of the expansion of space, an expansion of the size of the universe. So the idea that there might be a fifth force responsible for the expansion of the universe, like i.e. dark energy, it has been explored, especially by the people at Dartmouth. It hasn't been a super fruitful avenue of research. It seems like the obvious thing that, gravity, which we know can cause the expansion of the universe, is most likely responsible for what we view to be the effects of dark energy. But it's not completely ruled out. So yeah, if I was going to place my money, I would say that dark energy is a gravitational effect. But there is some small chance that it could be due to some fifth force.
Fair enough. Fair enough. Tim, any comments about that? Or
No,
we
I
can
think
move on?
that's a good summary. I mean, in particle physics, you got to be. I mean, it's okay to speculate, but you also got to be somewhat economical in your speculation, because Einstein's theory is already able to accommodate dark energy, although it's just a number. But we still have to explain that number. There's sort of no reason to add a new force because gravity is already able to accommodate that. That's not to say it's impossible, right? It could be that, hey, there's an extra force that kind of acts like gravity, but somehow it's not gravity. You could speculate that. I mean, that's the beauty of physics and science, right? You could dream up a scenario as long as it's backed up by data, then it's good. But also in this regard, we don't have a lot of data on dark energy other than the fact that the universe is expanding and the expansion is accelerated. In order to have the telltale sign of discovery, you're going to have to be able to hit this dark energy field if it exists and somehow create a dark energy particle out of it. And that's basically daydreaming, right? Like, I don't know. We're never going to be able to have that technology to do it. So unfortunately, even if it's plausible, we're never going to see the results. I don't know how many lifetimes, probably never for human technology. So it's just not economical. It's not to say that it's implausible, but like kind of like, well, sure. Then what, right?
Yeah, that's really fair. So, there is an audience comment that's fairly technical, but before I get to that, like it's probably the most technical audience comment I've ever seen. But before I get to that, I want to give you guys a chance to leave any final parting thoughts, and then we'll have this like
Wait,
super
what?
technical hour after. But go for it. Leave
Yeah.
the parting thoughts.
Okay, my final thought would be just that, like, it's ridiculous to assume. I think it's downright arrogant to assume that there's only four forces. Um, the fact that we've discovered two out of the four so recently, and suddenly you decide, oh yeah, I guess what I've seen so far is all there is. That's crazy. Let's not think that.
Yeah, I mean, I would agree. Like, four is a very arbitrary number. It's an observational fact that there are four fundamental forces, but it's very hard to believe that that's really the final number, right? I mean, back in the days, people thought there's only protons and electrons, right? But lo and behold, we found quarks, we found neutrinos, we found things like muons and taus. And I think famously one of the physicists said when we discovered the muon particle, I think was it Feynman? Like, who ordered that, right?
No, it was Gelman.
Gelman, maybe,
No,
yeah.
oh, I don't know.
Don't quote us on that. But in the same vein, like, who'd ordered all that? Like, we have so many particles that we don't need, really. And I bet you they are additional forces. Like, why not? And it's just because those forces don't tend to linger around, right? They will decay or whatever. So for a variety of reasons, I think it's my money is on that. There's definitely a fifth force, probably 6, 7, 8, many new forces. And the only question is where to look for these forces. Where should we? I mean, the question is practical, right? Given that they're probably new forces, where is the best place to look? In what corners of of our theory is that we have the technology capable, and to be able to discover them and make a discovery. So I think that's where the frontier of science lies, and I think that's a very hot current research topic.
Yeah, that's well said, well said. So,
Okay, what's the question?
right. Yes, it was not a question, it's just like a bunch of statements, and I'm just curious what you guys think. Okay. For everybody else, apologies for all the lay people in the audience. The gauge group of the standard model is U1 cross U, SU2 cross SU3, and it can be shown that it's isomorphic to R times C times Q times O, which are the multiplication of real, complex, quaternion, and octonion. Cole Fury showed that R times C times Q times O can explain all the standard model particles with their spin and charge and the three generations and just that and not any other particles. It is very hard to believe that it is accidental given the fact that there are no greater groups than octonions. Other forces or particles we may need to have a greater gauge group like SO10. I don't know.
Yeah.
Jim, have you ever heard of this? I've never heard of this isomorphism between the standard
So,
model and RCQO.
yeah, I don't quite understand what this is, but let me just add that, you know, the idea of unification, it's nothing new. It started with probably Howard Georgi, one of the seminal paper, to show.
No, it started with Weinberg.
Probably early. I don't sure earlier, but
Weinberg, yeah.
But you know, for many years, people have suspected that the quarks and the leptons and the and the neutrinos and all that fit in some type of pattern, right? And there are many theories that propose elaborate structures, many different groups, and I suspect this is just one of the many. And the key, I would say, the devil's in the details. You know, back in the days, people thought Howard Georgi was going to get a Nobel Prize when we discovered proton decay, because that's one of the predictions of unification. That did not happen, right? And then
we never saw proton decay.
Yeah, exactly. We never saw proton decay. So the bar has kept move higher and higher and higher. And now what we started with a very tantalizing model. Now then you have to add extra jazz to make it palatable again. You have to add, for example, you know, sometimes you have to add supersymmetry to make sure the strength matches up. Then you have to add extra dimension to make sure the proton, you know, and all kinds of jazz to make sure maybe the proton doesn't decay as quickly as possible. And there are also problems with, you don't want to create a lot of monopoles that mess up your universe. But once you add in all those details, now the model is not palatable anymore, right? Like you have all these beautiful structure, and then all of a sudden you add all this complicated stuff in it. Now you have to add A, B, C, D, E. It's not so simple and beautiful anymore. And I would reckon that many of these theoretical proposals, the devil's is in the details. Is to calculate out what are the consequences with experiments, how that conforms to many of the experiments we've done, and then we'll see that, hey, it's not as nice as it seems. But I would add that it's probably because we lack the imagination. I would say, like, nature is the boss, right? Probably we don't have the best ideas yet, so it remains to be seen.
But also, I'm really skeptical about this claim that U1 cross SU2 cross SU3 is isomorphic to the real numbers cross the complex numbers, cross the quaternions, cross the like. I worked on grand unified theories, and I've never heard of such correspondence, and I don't even know what that really means. To be honest,
yeah, and also octonion is non-associative. It doesn't exactly form a group. So that statement itself, so that statement doesn't really form the basis of a gauge theory. So, you know, I would say it's at best not like a mainstream idea. So
no, there's no way that are like, yeah, these are not even groups. How do you tensor product them?
Yeah, it doesn't quite exactly make sense. So I mean, yeah, I think to answer some of these audience questions, unfortunately, it comes down to the technical details. We need to see like a peer-reviewed paper, how a faithful calculation is carried out to the experimental consequences, and then see, if the physicist has done due diligence to check many of the experimental outcomes that we have. And unfortunately, look, like, I know that a lot of times we talk in colloquial terms. It's like this idea versus that idea. But particle physics is actually pretty darn hard, right? Like Mikey said, you work in unification. There's a lot of homework you got to do before just not tossing an idea right to the trash bin, right? Like every day you probably come up with 10 to 20 ideas. Just most of the time it's just straight to the trash bin because they don't work.
I mean, I love octonions, and I've been striving to find a way to connect them to something real in particle physics, and I haven't heard of any like real like octonions. If not, like there's some intriguing
Yeah,
connections, like you write the Dirac equation in terms of octonions or something. But like for gauge groups typically relate to octonions. I've never heard of anyone reputable making such a claim.
yeah.
Even Greg Moore, like I don't know.
Uh,
I'd
well,
love a reference though to that. Yeah, if you have a reference about this isomorphism between gauge groups and octonions, that'd be fantastic. Like if it were
Yeah,
true,
sure.
it'd be the most shocking thing of the century, and for sure be a Nobel Prize. But
well, we need experiments, but share it into the channel. If there's a reference, we'll try to make a comment.
yeah. I haven't kept up too much, in the last couple of years, but yeah, be glad to read it.
yeah, the audience member is saying please check her paper. I can send you guys the name. But yeah, if you to the audience member who asked this, if you have further questions or want to have a discussion, do join our Discord channel, and we're happy to like duke it out
Yeah,
there.
totally. Yeah, we can chat about it there.
Yeah, absolutely. All right. So, well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Bye bye.
Yeah.